Okay, Ines? Yeah, great. Hi, welcome to this extra colloquium. Today we have Guilherme Franzmann, who's coming from Nordita in Stockholm. And Guilherme is a good friend of mine who I met in Japan 6 years ago. We were both doing a postdoc at the Yokawa Institute of Theoretical Physics. Before that, he was at McGill, working with Robert Brandenberger. And then he moved to Stockholm after Japan. And additionally, Guy does, well, he started off doing string cosmology, but now he's branched into many other things, and he's one of the deepest thinkers that I know. And currently, he is working on spacetime emergence, which you'll hear about today. But we've also started a project on things like the Hubble tension, which we talked a bit about a few weeks ago when I gave a talk here. So anyway, that's enough from me. So Guy, take it away.
Thanks for the nice introduction. Thank you all for coming. Quite nice to be here. My first time at the Higgs Center. Anyway, so today I'm going to be telling you a story of emergence in physics, and then more applied to space-time emergence. But as I said, it's going to be a story. And as any good story, there is some mystery. And so our first chapter of the story is about a mysterious box that we'd like to understand. If you can move the cursor, please. This way. I can. Thank you. Okay, so imagine that you are, as you are, a very good theoretical physicist and a very good experimentalist. And that's kind of like already a sign that this is a story, because I'm not sure how likely that's the case in general. But anyway, so you go to your lab, and suddenly you find that there is a mysterious black box in your lab. So you try to open the box, and you don't quite manage to open it. But the box has a display, which is an energy spectrometer. And so you can actually play with the display and see all the possible energy levels of whatever is inside the box. Now, as I said, you're a very good experimentalist, a very good theoretician. You have a lot of experience modeling physical systems. So you have a clue that maybe you know what could possibly be the system inside of the box. So your first guess is to imagine that you want to model whatever is inside the box with a lattice of spin. And I'm not sure everyone has experience working with writing down an Ising model, but everything you need to know is that when you think about spins, basically you have three different sort of freedom. You can actually orient them in the X, Y, Z direction. And you also know that once you have a lattice, you can actually do different things with your spin sites. You can couple them. Usually we think about coupling neighboring spins. So you can have first site and second site, and they are coupled. And you imagine that you couple that with some strength J. But you can also put your spin sites under some magnetic field. So you know that if you have a magnetic field H, it couples like H times the spin orientation of that particular site. And so by using those building blocks, you decide to postulate that maybe what's inside the box is this. Somehow there are 4 different spin sites. They're all coupled with their neighbors on the orientation of the Z-axis. And there is also some external magnetic field also on the Z-axis. You decide to postulate that it's 4 because you counted how many energy levels you could see in front of the display of the box. And you know a little bit about how those things actually can be mapped into different degrees of freedom that you can have. And with this particular model, you run the numbers and you find that H and the J that actually matched precisely what was on the box display. So you get quite excited. And typically when people are quite excited, they go and tell their friends. So you run out of the lab and you find a friend and you tell them the story that there is this black box and you were able to actually find precisely what's inside the box. And as you're telling your friend the story, your friend is like, no, stop. Because they also want to have their try of figuring out what's inside the box. Your friend goes out of the lab, starts thinking about their own model. They're also very good. Not surprisingly, they also come up with a model of what's inside the box. And at first, it looks exactly the same as your model, but if you pay more attention, actually, it's not quite the same. because the coupling between the neighbors is with H, which was what you thought was the magnetic field. And the magnetic field is now actually in that other direction, is on the X direction. And it's given by what you had as your coupling, J. And besides, a single site also has another extra magnetic field on the Z direction. And with the same J and the same H as you had, you arrive at the same spectrum. So you gather with your friend and you start talking about that. What is happening? What is a system that is inside the box, in fact? And after talking with your friend a little bit, you decide that actually there is a way of relating what you called a spin site and what they called a spin site, and how you called what you call magnetic field and what they called the strength of the coupling, and vice versa. And so you come up with this table. And it looks a bit complicated at first, but if you follow all the relationships of this table, you can actually precisely show that the two models are actually completely equivalent. And let's focus on two parts of what's happening here. For instance, you see that the parameterization of spin site number 4 on the Z direction actually in your model corresponds to all the spin sites, the degree of freedom on the X direction. Similarly, for their spin sites on the X direction corresponds to pairwise of your spin degrees of freedom on the Z direction. Now, this is of course a bit puzzling because when I say spin site, what is a site? Usually something that you think it has a particular spatial location, it's localized. But then you see that you have different models which have very different sense of localization of whatever might be inside the box. Now, formally, this is what's called a duality. And if you had n spin sites, you can actually write the precise Hamiltonian of each model. And you can precisely write the transformation between the degrees of freedom of each model. And then you can prove that the both Hamiltonians have exactly the same spectrum, that there is no way to tell apart which one is which. But that's exactly what we'd like to understand. What is inside the box? How could we actually ever find out what is the real physical system of what's inside? And now, typically what we do when we want to find what's inside of anything in physics, well, you go thousands of miles further south, you go to CERN, for instance, and you smash the box, and you try to see what's inside, right? But what if you cannot ever open the box? How do you approach this problem? How do you even think about it? And we saw, basically, different models are telling that there are different notions of system inside the box. There are even the different notions of what's interacting, what are the fields that are inside the box external to your physical system, and also different notions of neighboring sites. The very notion that we would like to think about what is the spatial distribution of your physical system seems to be not well defined. And so how do we make sense of that? Well, we are in a story, and then you can go on a side quest. And the side quest is maybe to talk to a philosopher. So you talk to a philosopher and start thinking about how do I think about those more philosophical, kind of metaphysical questions. And maybe some of you know, there is what philosophers call the Wikipedia that actually worked, which is called the Stanford Encyclopedia of Philosophy. And there you can find entries on ontology. And ontology in philosophy is what people call the study of what there is, and also the study of the interconnections, the relationships of the different things that there are in the world. So we need to actually go back and start thinking more about this kind of question to understand how we can ever answer about what's inside the box, or how to think about that if there is some ambiguity. And to do that, we need to remind ourselves how we developed our intuition of what we think are physical systems in first place. So in the next chapter of the story, we go all the way back and quickly start reconstructing what we think that does exist and how do we think about physical systems. So we start going all the way back to Newton. And if we are like in 1687, and Newton is postulating, is writing his Principia Mathematica, and you open the book, and you open book 1, And you start seeing already a few hints about what are the implicit assumptions of the theory. And as you have probably most of you know, two of the assumptions were written down that had to do about time and space. So Newton had written absolute true in mathematical time of itself and from its own nature, both equally without relation to anything external. Similarly, absolute space in its own nature, without regard to anything external, remains always similar and immovable. So suddenly we start off with classical mechanics already assuming an absolute notion of both time and space. And this is an instantiation of current of thought called substantivalism. The idea that space and time exist as independent substances, independently of any material content of the universe. Now it's already interesting because not only we're talking about space and time, but also in relation to anything else in the universe is material content. So there is also material content. And typically when you think about classical mechanics, the material content, we start off with a simple point particle. So we have a space-time, we have our point particle. Typically the point particle has a state. So we call it, or we define the state in terms of the position and velocity. And it has an evolution equation, Newton's equation, as all of you know. And this seemingly looking quite formalism is actually very powerful, as you know, because classical mechanics is actually deterministic. If you were a Laplace's demon and you knew precisely the position and velocity of a single particle at any given time, you can predict and predict precisely the trajectory of the particle. Now let's see what happens when you try to apply this to a physical situation, right? So we can think about using classical mechanics to describe the orbit of Earth. Now, Earth is not a point particle. There's around 10 to the 50 different particles composing Earth. So in principle, you'd imagine that this would be an impossible task to achieve. But as most of you have done when you were doing undergrad, we have a trick. And the trick is that you go to the center of mass of the planet. And then suddenly you go from 10 to the 50 particles to a single point particle, the center of mass. And then from 10 to the 50 times 6, 3 positions, 3 velocities, you just have 6 degrees of freedom that you have to specify, the degrees of freedom of the center of mass. And moreover, not only that, but this Newton equation is still the same. So the center of mass is following the same equation that you had before for each of those point particles. So what has happened here? How is that even possible, right? And that's where our story of emerge starts. Because to some extent, this is a very mild case of emergence and us being able to describe things in an emergent manner in a consistent way that's actually reliable and predictable. So let's define better what we mean by emergence throughout this talk. It will be quite useful later on. So we're going to think of emergence as the following. We understand it as appearance in a certain description of a physical system of properties that are novel with respect to a different, quite often more fundamental description of the same system. But those properties are also robust in the sense that they enable us to have new predictions of the behavior of the system that perhaps we wouldn't be able to achieve before. Moreover, quite often, emergence requires some sort of limiting procedure or even possibly some drastic approximation so that you can actually see and study those novel properties of the system in this new description. Okay, so let's try to abstract a little bit more and formalize this to understand what happened in our previous example. So let's go back to when we think about classical mechanics, somehow we can categorize different things that are in the theory that we just saw so far. Somehow there is the idea that there is a background space or space-time. We also talk about different or some sort of degrees of freedom. In the case so far was positions and velocities associated with each particle. Of course, there is a notion of observables that I won't touch so much about it, but we can also talk about that. The different things you can measure about your system. And there is dynamical equations. In our case of classical mechanics, that's Newton's equation. What happened in our case of the center of mass motion? Well, basically we went from having a space-time, 10 to the 50 particles, some sort of observables that are functions of those particles, degrees of freedom, and Newton's equation for each of those different particles to condensing all those degrees of freedom into a single one, but the sort of observables and the sort of equation of motion that you had before, it still remains, similarly to the background spacetime. That's what we're going to be referring to level 0 emergence. Because it's very mild. The nature of degree of freedom hasn't changed. The evolution equation hasn't changed. The background theater hasn't changed because we still have the same kind of spacetime. But we still can already start thinking about questions that we can ask if we're going to bring us back to our mysterious box, that we still have to kind of like figure out what's happening there. Well, the question that we can ask, for instance, in this situation is, does the center of mass exist? Because we started with our classical mechanics, and we said there is time, there is space, there are point particles. But suddenly we have this new thing. It's made of those point particles. And we can ask the question, well, to which extent we should think that these are actually existing? And there are different ways to answer this question. The approach that I'm taking here is to say that, well, in this particular example, for sure, there is at least inside the planet a material particle that basically instantiates the trajectory of center of mass. So from that point of view, there is a material instantiation of the center of mass, degree of freedom or particle. But of course, that's not always the case. Sometimes actually center of mass between different objects can be completely in empty space if you want. But then still you can rely on the idea that we are having this substantivalist perspective in which, well, whatever point in space it is a center of mass, it does exist because space absolutely exists anyways. All right, so let's move on to a more interesting case of emergence. Let's think about when you go from particles to gases in a situation of equilibrium to make it simpler. So if we're in this room here, there is probably around 10 to 24 different particles, each of them with their positions and velocities. But if we're close to equilibrium, we condensate all of that into 3 different variables. We talk about the pressure, the volume, and temperature. And our evolution equation that was the Newton's equations for every particle becomes now even not a dynamic equation anymore, but a correlation equation between the pressure, the temperature, and the volume of a given room. And as you know, the temperature and the volume and the pressure are actually defined in terms of the average mean square of the velocity of each particle. Okay, so what happened here? Let's go back to our scheme we had before. When we look to our scheme, something a bit more drastic has happened. That's what I'm calling level 1 of emergence. Because now, not only the degrees of freedom have been condensated into a much smaller set, but their very nature has changed. Right? So we go from vectors, such as positions and velocities of momenta, to now scalar fields such as temperature and pressure across a room. The sort of observables also changed. We're going to be talking about computing the entropy or the heat capacity, so on and so forth. We have a different equation. We have, for instance, in this particular case, the ideal gas law. But one thing hasn't changed. It's still our background theater where those things are actually happening. And again, we can ask similar questions that we had before. For instance, we can ask, well, does the temperature exist? We make sense of temperature in this situation. But then we can actually resort back to our definition of emergence. Because in the end, regardless of how much sense of existence we want to think of the temperature, we can still say that, of course, the temperature is an emergent quantity, because by defining this new degree of freedom allows us to be predictive. It is a robust new quantity that allows us to make predictions about what might happen in a room, for instance, if we change the volume or the pressure, so on and so forth. Okay, what else can we do? Well, here the ideal gas law was actually proposed in 1872. That's where we are in our reconstruction of this story of emergence. And perhaps quite coincidentally, a year later, there was a paper on Nature by Riemann, actually, where he was already hinting perhaps as how we can actually move forward. And so we can have a look on what Riemann had to say. And so this paper is called The Hypotheses Which Lie at the Base of Geometry. And he says, the questions about the infinitely great are for the interpretation of nature useless questions. But this is not the case with the questions about the infinitely small. It is upon the exactness with which we follow phenomena into the infinitely small, our knowledge of their causal relations essentially depends. It continues. Now it seems that the empirical notions on which the metrical determination of space are founded, the notion of a solid body and of a ray of light, cease to be valid for the infinitely small. We are therefore quite at the liberty to suppose that the metrical relations of space infinitely small do not conform to the hypothesis of geometry. And we ought, in fact, to suppose it, if we can thereby obtain a simpler explanation of phenomena. So that's quite impressive, I find. This is 1873. He's putting out not only the notion of geometry, but also the notion of solid bodies, or even like ray of light. So I guess only someone like Riemann had the genius to have the foresight to somehow already anticipate what would happen 30 years later. Which brings us to our next chapter, of course, quantum mechanics. So with quantum mechanics, we start off with a very similar structure as we had before. Because we also have some space, we have some kind of states and degrees of freedom, and we had some evolution equation. But right off the bat, as you know, the underlying notion of space is not space-time anymore, but actually it's a Hilbert space. The degree of freedom is, of course, not anymore the degree of freedom in phase space, but actually it's the wave function. And we have a very different evolution equation, which is intrinsically linear. The fact that the equation is linear means that actually you have a superposition of different solutions. And exactly that leads to the departure from the minimalist formulation of quantum mechanics in comparison to classical mechanics to other things that actually we don't quite find analogs. In mechanics, we have the Born rule. So the new degree of freedom, the wave function, is actually giving us probability distributions of possible observables and observations we can make in the lab. Similarly, as I said, the fact that the equation is linear means that you have a superposition of different solutions, but upon measurement, it seems that we always have this notion of collapse. We single out a given solution. And those things are, to this day, hard to understand, and people work on trying to make sense of that. Now, regardless, we do believe that quantum mechanics rules the microscopic world. And now the macroscopic world, the big world, we believe to be made of the small things. And so we expect that no matter what, the world seems to be fundamentally quantum. But if that's the case, now it seems that we turn things around, and suddenly classical mechanics is not the base theory anymore, but should be seen as the emergent theory, in the sense of like there is this classical quantum limit. Somehow classical mechanics should be a limit of quantum mechanics to some extent. And so if you bring back to our scheme we had before, now we had what I've been calling emergence level 2. So not only the degrees of freedom from quantum mechanics to classical mechanics, the kind of observables and the evolution equation changed, but also the background theater. Now we have something happening in Hilbert space in quantum mechanics that somehow is encapsulated or encoded in space-time at the emergent level. Okay. Now, before we're discussing about temperature, center of mass, do they exist, do they do not exist? And so naturally, we can extend that question now to space-time and to the degree of freedom that we had in classical mechanics. And suddenly we see that perhaps what we should do is to go from our classical mechanical ontology of what we thought were the physical systems, what we thought exists out there in the world, to this lower level, in which everything is defined at the level of quantum mechanics. So somehow, in another way, you can think of when we said before the study of what there is, well, now we realize that actually that verb to be in there is was carrying somehow an adverb after, because it was saying to be or there is in space-time, but also now we have to think about the verb to be in Hilbert space, in quantum space. And we have to have this distinction when we talk about things somehow existing, either in one space or in another space. And the question is, can we let go of our classical ontology? And we think of the verb to be only basically in quantum space, in the Hilbert space. And this brings us to our next chapter, which is to show in a very schematic way what would be the status of art. How do we think about those things in the context of algebraic quantum field theory? And that's something that can be quite actually formal and abstract. So I'm going to try to be as pedagogical and simplistic as possible to actually convey the idea of what is actually going on when we think in those terms. And so let's start. As we've been discussing, we have space-time, and we think to be here. We are in space-time, and we go around and go to the lab, and we make measurements, we make observations. And basically, measurements, observations are, to some extent, counting numbers. You're always like seeing numbers, and quite often they're not very sharp. So usually you have actually a distribution of what you actually go and observe in your lab. You have errors, right? It's not always the case when you are in a room like this, but in principle, we don't have access to infinitely sharp observables. Now, we want to go from that space to say that actually what there is and how we should think about things is in terms of this underlying Hilbert space. You would imagine that space-time actually is completely superseded by this Hilbert space. And so how we think about now things that are in space-time in terms of things that are in Hilbert space? Can we make any clear association? Well, one way to think about different things is you have to have a criterion to even be able to distinguish between what seems to be different. And as probably most of you know, in the case of space-time, we typically rely on this notion of spatiotemporal locality, which is the fact that in space-time, you can think about space-like regions. And if they are space-like, in principle, there is no way to exchange information. And that's at least is one of the criteria you can use to reliably say, of course, what is in region U and what is in region V are distinct. So that's good. We have a way of telling things apart to some extent in space-time. And the question is, can we push the same kind of localizability or bring that to this Hilbert space, to our underlying quantum space? Can we have this? Can we have each of us in different space-like or causally disconnected regions have our own label, our own tag of smaller Hilbert spaces that we carry around with us in a way that we can meaningfully talk about my own Hilbert space and you can talk about your own Hilbert space, and I go to the lab and I do a quantum experiment and I know that what I'm doing is actually the lab Hilbert space, so on and so forth, which is tacitly what's implied in any paper that probably you ever read about quantum information in quantum mechanics. Well, if that was possible, we have something very nice, because suddenly we realize, okay, we talk about this verb to be in space-time and the verb to be in Hilbert space, but actually there is a bijective way of relating them. And so we can just think about to be in the end. We don't have to make this distinction, right? But if you remember how we start our story, probably you should already expect that you cannot actually expect this to happen. The beginning of the story was exactly saying that somehow we had different ways of localizing, of thinking about spatial distributions of systems quantum mechanically inside our box that was ambiguous. And so that's not possible. So what do we do then? Is there anything else that we can do? And there is. And typically what we do, we introduce other abstract spaces that are not often discussed in a quantum mechanical course, but if you have been doing a bit more formal quantum field theory, for instance, or even quantum mechanics, you might be familiar with it. One other space that we introduce is what we typically call observable space, which is a space associated with the algebra of observables, given a quantum system. And in that sense, for the observable space, you do have a notion of locality that somehow is retrieved from our spatiotemporal locality in space-time. So you can imagine you are in your lab in region U. Basically, this is kind of like encoding all the devices you have around you. You carry with them, and those are yours. They're independent of the device of other people somewhere else in the galaxy, for instance, and whatever they are doing there. There is another space that we also use that also carries a notion of locality. which is what people call usually state space. So again, around your own region, you can devise an experiment and make measurements, but to some extent, you can also think about states in which are around you for your physical system as independent. And so now we're kind of set, because suddenly we can think about preparing a system in my region of spacetime and making a measurement in that same region. And that's precisely what you'd expect to actually give you some numbers. And the final question here is to imagine, well, are those numbers which are being produced, are the correlations that are coming from combining observable space and the state space, the same kind of correlations that you actually do measure in your lab? Is that actually what happens? Because at the end of the day, none of these seems to be available to us. I go to the lab and we have our experiments and we build them and they are located in space-time and my measurements are located in space-time and my tables that I write down, my data is my space-time. So how do I know, how do I actually infer and make all of this machinery work, right? Now this, needless to say, was noted by our founders of quantum mechanics, and we can actually see a quote from Bohr discussing this problem. So what Bohr had to say? Well, it is decisive to recognize that, however far the phenomena transcend the scope of classical physical explanation, the account of all evidence must be expressed in classical terms. The argument is simply that by the word experiment, we refer to a situation where we can tell others what we have done and what we have learned, and that, therefore, the account of experimental arrangements and of the results of observations must be expressed in unambiguous language with suitable application of terminology of classical physics. Maybe in less convoluted way, because Bohr was famous to be somehow prolix. We see the quote from the book by Landau and Lifshitz. Thus, quantum mechanics occupies a very unusual place among physical theories. It contains classical mechanics as a limiting case, yet at the same time, it requires this limiting case for its own formulation. Remember when we saw back our definition of emergence, we talk about limiting cases, but we never expected that somehow the base theory should also be formulated in terms of the limiting case. Seems to be the case when we unavoidably talk about quantum mechanics. And so suddenly we start understanding a bit better what happened with our box example. Because if we only have access to things which are at the classical realm, all the way here, perhaps the machinery that we are using to describe our systems are ambiguous. Perhaps what I thought was my localization of my observables in the observable space and my states in state space is ambiguous after all. And that's our maybe way of starting to understand the whole mystery of the box. Because the box was basically saying that different descriptions, we had different ways of defining what were the observables, being, for instance, the different spin sites or the way to couple them, and the state preparation of what's inside the box, that was ambiguous. And it was ambiguous because we are actually constrained at that particular level. So to some extent, very similarly to what we have when we talk about gauge freedoms, there seems to be some kind of redundancies in the way that we're going to be building our quantum mechanical descriptions of what's happening under the hood. Okay, so we understand a bit better what happened with our initial mysterious box. The mystery, to some extent, is resolved. But as any good story, we not only have the mystery, but there is also a villain. And our villain hasn't showed up so far, but probably as most of you could imagine, what about the gravity? So far, I only talk about, we had spin sites and quantum mechanics, we talk about particles, gases, quantum mechanics, but I never mentioned the word gravity. So how much of this picture that we had so far holds water when gravity is also part of, or also relevant for our physical systems? Now, as you know, Einstein proposed special and general relativity and changed dramatically the understanding of gravity. But to understand a bit better what he had in mind when he thought about gravity and proposing general relativity in particular, we can actually go back. We can go back to 1920s and see what he wrote about it and see what was his understanding of actually what was happening when gravity was, or when GR was proposed. So this is a paper by a historian. It's called Why Einstein Did Not Believe That General Relativity Geometrizes Gravity. Very interesting paper. I highly recommend it. It goes against the lore that GR is about geometry and how Einstein actually didn't quite think in that particular way. But anyways, in this paper, there is one of the quotes by Einstein where he says, the systematic decoupling of basic geometrical concepts, straight line, distance, etc., from the bodies of experience, of which they are abstract representations, must not let us forget that in the end, geometry is supposed to tell us about the behavior of the bodies of experience. If there were no practically reached bodies that can be brought into congruence with one another, we would not speak of the congruence of distances, triangles, etc. It is clear that for the physicist, geometry becomes meaningful only as he associates bodies of experience with those basic concepts. For example, by associating the concept of distance with a practically reached body with two markings. In other words, Einstein is opposing that substantivalist view that we saw that was implicit, assumed in Newtonian mechanics. GR is actually based on a much more relationalist view, where space and time do not exist as independent substances. There is only the material content of the universe. Space and time are merely defined through spatiotemporal relations among the material objects in the universe and their parts. Space-time is thus a constructed relational complex of relative positions of material objects. Now, for the people who of course have worked with GR, you know that actually general relativity doesn't quite push this project all the way, because in fact, in general relativity, you do still have vacuum solutions, for instance. So there is still a notion in which space-time does exist, regardless actually of you having not material things contained in your universe. But anyways, so as you know, it's quite hard to bring gravity into quantum mechanics and have a coherent picture of both of quantum gravity. So we have learned quite a few things on the way. And some of those lessons actually are quite useful to understand what happens with what we had discussed so far regarding emergence and regarding how to think about different physical systems located in space-time. So let's see a few lessons or a few things that we know about gravity, both classical and in the context of quantum mechanics. I'm going to quickly talk about the notion of universality, the notion of operational measurement limitation, a crucial notion for us here that there are no local observables in quantum gravity, and how that leads to the notion of holography. And then we go back to our heuristic picture of algebraic quantum field theory and see how much of that actually can be carried on when you have gravity. Okay, so let's start with universality. As you know, gravity is universal both in scope and universal strength. So not only everything, including gravity, couples with gravity, the scope is universal, but also the strength, at least in the way that we understand nowadays classical gravity, we couple everything in under the same prescription. And this kind of universal behavior is also noticed in other areas of physics. In particular, Feynman made an observation about that in the context of perhaps hinting that gravity should be expected to be emergent from something else. Feynman observes that the fact of universal attraction might remind us of the situation in molecular physics. We know that all molecules attract one another by a force which at long distance goes like 1/r⁶. These we understand in terms of dipole moments, which are induced by fluctuations in the charge distribution of molecules. Well, one possibility is that the gravitation may be some attraction due to similar fluctuations in something. We do not know just what. So it's known that in molecular physics, there are universal kind of forces that are emergent from a microscopic description in terms of something else, those charges here in this case. And one would expect that maybe something similar would happen for gravity. Okay. The next lesson is the fact that we do have some operational measurement limitation in gravity. As you know, if you want to see at smaller scales, basically you have to crank up your energy so you can see it have enough resolution to see what's in there. But as all of you know, if you start increasing the amount of energy localizing space-time, at some point you hit a limit that actually produce some black hole, some small, very small black holes. And if that happens, operationally speaking, you just don't have access to this fine-grained structure of space-time anymore. So from this operational point of view, it's actually not even clear if there is any sort of space-time, at least in the pragmatical sense, if you try to zoom in all the way. The other lesson that we have, which is the most relevant for us, is that there are no local observation variables in quantum gravity. And here I'm being very qualitative, but the idea basically is to say that we know that the most dense objects that we can have in space-time and that can store information in the most dense possible way are black holes. And the problem with black holes is that not only they are the most informatic dense objects, but also the way that they store information is actually finite. And so if you were in your lab trying to devise an experiment to have an infinitely sharp measurement of anything, you actually would find that at some point you reach a bound, because you cannot go over the amount, or you cannot go over the information density that a black hole itself can actually have in space-time. Unless we could try something else. We could imagine that somehow your lab, as you're making your measurement sharper and sharper, your lab is becoming larger and larger. And so the information is becoming encoded in larger and larger regions of space-time. And if you're gonna go all the way to infinitely sharp measurements, you'd have to bring your lab to be distributed all over space-time. And that's the qualitative way that you can think of how holography actually naturally emerges from classical gravity. And so in that sense, there is no notion that you can think about localized, sharp measurements in the context of classical or quantum gravity. And that's how you end up with a notion of this distribution of information being coded all the way to asymptotic infinity of your space-time. So having that kind of a qualitative understanding in mind, we can go back to what we had when we define our status of art in terms of algebraic quantum field theory. And the main thing was that we rely on this notion that you have very well localized observables. But as soon as I bring gravity, suddenly I don't have that anymore. We just saw this heuristically. And so all this picture that we had so far kind of like goes down the sink, unfortunately. And so you have to start again. And that's really contemporary what people are trying to do when they think of how we can think about quantum gravity from an algebraic quantum field theoretical point of view. How can you define your observables, so on and so forth, in a way that somehow you can recover part of that formalism that we had before. And this is currently unknown in this topic of research. Another way of phrasing what's failing here in this picture is going back to the question that we had before about our box. We're trying to figure out what was inside the box, how can we make sense of that? But really, when you have gravity on and you think about basically what's happening in the whole, across the whole universe in a quantum gravitational way, that failure that we saw here is actually, in another way you can think of, as if actually all along we are inside the box. And we have to make sense of that. And that's why it's so hard actually to even think about define those different observables and spaces and state space to make sense of what would be reasonable to expect in a full quantum gravity theory. And so these are basically the heuristic way that you can understand what's actually going on. Which brings us to chapter 6 of our story. So now what? What do we do, right? Well, as you know, people are very creative and we're all trying different things. And we have a whole landscape of different proposals for quantum gravity, from pushing further classical gravity, having effective approaches, going through fundamental approaches. You know, we have string theory there, quantum gravity here, supergravity. You have pretty much everything that people are thinking about at any given moment. But now we can try to think from our construction of emergence, perhaps since we still don't have the answer to how it makes sense of that picture that we had just before, and how to think about emergence at that case, perhaps we have some general features that we can think of to help us to map this landscape of different theories and to somehow see what we can expect of them. And for this, we can rely on a classification that goes back to Daniele Oritti's paper a few years ago. So he has 4 different levels of classifying space-time emergence. The level 0 he doesn't quite talk about in his paper, but just a reminder that some people do think that gravity might just be classical. The main person is Jonathan Oppenheim at UCL. You might have heard of him. But anyways, if we go back now to theories which do not take gravity to be classical, there are different levels of what can happen. Now, the levels I've been calling 2.1 because all of them, or 2.1, so on and so forth, because all of them are going to be within our level 2 emergence that we had before. So we go from full quantum description to a full classical description. But there are different levels or different requirements that you have to impose in your theory to get all the way. For level 2.1, it's typically what people have in mind when you think about just quantizing GR. So your fundamental degrees of freedom are still geometrical. You quantize the theory. So your emergence happens in the sense that you have to take the classical limit. And you recover what would be a normal classical theory for gravity. For level 2.2, you imagine that actually your fundamental degrees of freedom are not geometrical anymore. They might be combinatorial, they might be algebraic, they might be graph-like, so on and so forth. And then not only have to think about the classical limit, but there is also the notion of continuum limit. How do you go from this very different kind of degrees of freedom to what we have when you think about the continuum in space-time? There is level 2.3. We still have the same sort of now non-geometrical degrees of freedom, but perhaps there are different phases that they can actually group together and reproduce. One of those phases might as well be our continuous space-time phase. You have to show that that would be part of your theory, but maybe the theory also allows for other phases which are not actually your space-time continuum phase. And finally, sorry about that. Finally, if you have different phases, you can also think of like, well, how do you go from one phase to the other, right? How do you have phase transitions? But from that point of view, things start becoming a bit tricky because I say, how do you go from one to the other? How do you make a transition? You see that my language is really loaded with temporal words. There is a directionality. But we're talking about space-time emergence. What do we actually mean by time and transition in this particular context? And so people also talk about non-temporal geometric genesis. So atemporal emergence of geometry itself, whatever that means, because of course we don't fully grasp or understand that. Having this in mind, we can actually also think about the different possibilities of theories and how they can connect with one another in the following. You can think of the space of space-time models, and here here is the models in blue that do have some underlying quantum mechanical description. But there's also possible classical space-time models that actually do not have any instantiation of quantum gravity theory that gives rise to them. Similarly, if we focus on the space of quantum gravity models, there might be the area which gives rise to space-time models in some limit. There also might be non-space-time quantum gravity models, whatever they are and whatever they give rise to. And our task somehow is to find things which are in this arrow, this more lengthy arrow, but having in mind the fact that it's unclear even if our current, for instance, classical space-time model, say general relativity, does have a fundamentally quantum gravity description. Perhaps GR is actually not in this set, but is in this set. It might be there should be another theory that somehow gives the proper classical limit, which can be recovered from a quantum gravity description. We don't know. But anyway, so since we are approaching the end, and since also we talked about atemporal or non-temporal geometric genesis, we go to our final chapter, and it's chapter whatever, because there is no time anyways, as we've been discussing just now. We can just make some statements about the notion of having time as emergent or fundamental. Again, trying to classify, having an underlying finite or infinite dimensional Hilbert space. Can we learn anything when we think about time being emergent or fundamental, just knowing that the Hilbert space is going to be infinite dimensional or not? I know that you can. Time is emergent, the Hilbert space is finite dimensional. Whatever we call universe, our classical universe, of course, had a beginning, because we just talked about those things actually having to emerge as a phase within the quantum gravity description. But if the Hilbert space is infinite dimensional, the universe may or may not have at the beginning, because in principle, you could imagine that this phase has already appeared and it has always been there. So there is no notion in which you can think of our particular classical description actually having a beginning. Similarly, if time is fundamental, but the Hilbert space is finite dimensional, then the universe is eternal because time is fundamental. But the region that you explore in this infinite amount of time is finite, so you expect that you should observe some recurrence. And one could even imagine if you have a quantum gravity theory, and it is a finite dimensional Hilbert space in your quantum gravity theory, that you could try to predict or find signatures of what would be a finite recurrence time of in your universe. And similarly, if the Hilbert space is infinite dimensional, the universe is also eternal, but perhaps you never observe any sort of recurrence. Anyway, so to conclude, first we have some thoughts. Just review a bit what we have seen. There is no space-time but matter. We also have questions about what does it mean to be matter, right? Matter typically was understood as something to be in space-time, but now we have to reassess what we mean by that. So we have to think better about the notions of existence and physical systems in this context. At the same time, we discussed that measurements, they do happen in classical space-time, as we saw with Bohr, Landau, Lifshitz, as you know. So it seems that one cannot let go of the classical anchoring and its role in defining the relevant ontology. In this paper by Euriti, as you just described, one has to accept a multi-level ontology of some sort, in which both fundamental and emergent properties and entities are real in an appropriate sense. Maybe you have to somehow simultaneously define your physical system, both classically and quantum mechanically, and understand exactly how they are related with one another. So to conclude, as you know, quite often progress can be made in science when obvious notions are put into question. Typical examples are led to relativity and quantum mechanics, Einstein thinking hard about the nature of simultaneity, and Planck thinking about the radiation spectrum being or not continuum. And another seemingly obvious concept that we discussed throughout the talk is the notion of what there is, but really what we mean by a physical system, either classical or quantum mechanically, and how they are interconnected. And I do think that current contemporary research in quantum gravity and foundations of quantum mechanics and gravity are hinting towards the fact that we do need to understand a bit better and scrutinize a bit better what we do mean by physical systems. If you really want to understand how we can think of the emergence of classical physics and also the emergence of space-time in the concept of quantum gravity. And I end here. Thank you.
Let's open up for questions.
It's online if people have questions there.
You seem to put a lot of emphasis on Hilbert spaces as being fundamental. But then you also mentioned algebraic QFT. One of the main lessons of algebraic QFT is that Hilbert spaces aren't fundamental. They're just representations, and they can be non-unique and messy. But I'm wondering why you put so much emphasis on Hilbert spaces.
Yeah, I'm trying to be a bit more pedagogical and a bit more understanding. But you're right. I will also say that at least from a global point of view, if I want to think that there is a global Hilbert space, and that I would claim that actually you can have a reasonable sort of unique definition if you want. But then as soon as you start breaking it apart and factorizing it, that you're running into all sort of problems that I wouldn't want to actually assign a Hilbert space to anything really, and I would just fall back into the algebraic description and just think about the observable space and about the state space.
questions?
Maybe the naive one, but you were like two slides, 3 slides ago, you were talking that you cannot kind of split between the quantum ontology and the classical. Why is that again?
Well, it seems just the fact that because our measurements are actually constrained to be always classical, no matter what, it does seem that however you want to define your physics, in the end, you seem to need to always make contact with the classical realm or space. And because your measurements are actually contained there and you don't have access directly to what would be the quantum space or in whatever context, either Hilbert space or algebraic sense, that may lead to ambiguities in the way that you're going to model your system quantum mechanically. And then you would have to think about those ambiguities in some way to actually deal with them before assigning any notion of localization, which is induced by your classical localization into your quantum system. But in summary, just going back to your question, is just to say that even if I try to do everything quantum mechanically, at the end of the day, I have to actually go and make measurements. And I only have
Classical communication.
Yeah.
Is there a way to like the classical communication also be emergent from some other quantum description? And if you have hyperspace and you have local operations and classical communications,
yeah,
and the local operations are there, and the classical communications would be some emergence or something else that you're just communicating the other system through, like photons or something that is emergent from that.
Absolutely. So that's why when I had my slide about quantum mechanics, I wrote collapse with scary quotes, because the language I've been using throughout the talk, it hints towards an interpretation of quantum mechanics, which would be more a Copenhagen or new Copenhagen interpretation. But you could imagine that actually everything is just evolving entirely, and then maybe you fall into an Everettian perspective, for instance. And then you have to, what I mean by classical in that context is just the fact that the world macroscopically seemingly looks like as if there is always a single outcome to every measurement. Now, either that's because there's a collapse of a function, for instance, or because we are in an Everettian world, and then you have to have the trouble of explaining how that seems to be the case. So for sure, you can extend the notion of what I mean by classical and what I mean by collapse in more general context, but then you still have to explain how it seems that the world looks like the way it does at what we call classical. Does that make sense?
Yeah.
But yeah, my final objective, or the way that if you would give a more research talk about this, I in the back of my mind, I have that there is only unitary evolution. There is nothing classical. And then I actually want to explain what looks like classical by using only unitary evolution. And then somehow you fall into a kind of more Everettian perspective.
Is this like somehow assuming that you could always have a closed system, like it's always unitary, you can, or could you have the evolution of unitary and there is a environment that you would never have access, maybe?
Yeah, for sure. That's also one way of approaching it. I mean, if you have, for instance, infinity Hilbert space, it could be that whatever we call to be our world is a finite region contained in that particular Hilbert space. And then you are always tracing out a lot of things that induce a non-unitary evolution of your system inside of your localized region Hilbert space. It could as well be the case if you still want to rely on this idea that through a region of space-time, you want to attach a Hilbert space. From that point of view, what's happening right now in the universe would be like that. We have Hubble horizon, for instance, and there is like things which are outside our observable universe. There are things which are inside our universe that are constantly going out our observable universe. And so you would have to trace the degree of freedom out, which could induce a non-unitary evolution inside the observable universe, if you want to define that as a localized Hilbert space, in the sense of having a Hilbert space attached to the observable universe and a Hilbert space attached to the outside of the observable space. The problem is that, as I said, we know that that doesn't work. You cannot do this separation in general. You can meaningfully talk about the global Hilbert space of everything there is, but you cannot take regional space-time and start attaching to them smaller Hilbert spaces that all glued together give you the global Hilbert space. And that's why then you go back to what I was commenting, that you have to do not rely on the Hilbert space.
So that Feynman's thought about how you get the 1/r to the 6th atomic for a whole bunch of different types of things. And he made this analogy with gravity. Is that a serious suggestion, given that general relativity, the 1/r squared is Newtonian, right? I mean, so why was Feynman saying that, given he knew that there was something beyond Newtonian physics? And is there anything deeper in that?
Yeah, I'm not sure. So it's a good question. I'm not, I would be lying if I would say that I'm fully aware of the context in which this quote is extracted from. I mean, we know, for instance, like you could imagine like perhaps what I don't have anything like geometry, I just have a spin-through field, and I actually give rise to what would be this universal kind of attraction and scope. But it turns out that when you try to do consistently a spin-through theory and you want to couple high orders, you have to sum an infinite hour of high order terms, and you resum back into the Einstein tensor, for instance. And so from that point of view, you could imagine like, okay, yeah, there is a spin-through particle actually that's giving this rise to this force, but when you try to do that consistently, then you fall back into the geometric picture. That's all I can say. I think the declaration is much more about the fact, yeah, what else there is universality.
It's more of a what if kind of question rather than
Exactly.
serious. Yeah, okay,
Yeah.
fine.
So,
Do you think mass is fundamental or emergent?
Very good question. I mean, it's going to be opinion like answer. But if you're going to try to really think hard about this question, right? So first of all, it's going to depend, for instance, like do we expect that if there is a global Hilbert space, is it finite dimensional or not? Or if it's not, then you cannot actually represent the Poincare group, for instance. Now, mass and spin would be the quantum numbers of your Poincare group. And so do you have Lorentz symmetry or not fundamentally? Or if you do, then you expect, yeah, mass is just another quantum number that's going to be there anyways. But if you do not, and I would be inclined to say that probably it's not, because I also want to let go of this geometric picture. I don't think that the Poincare group should be something that should be demanded from this lower level description. It should be an emergent thing. From that point of view, I wouldn't expect mass to be actually fundamental. It should be an emergent degree of freedom. But an emergent of what and how? That's the question. I have no idea how to. I don't know how to think about that right now.
Yeah. Well, we can wrap up. Can thank Guilherme again.